Hi guys, in this opportunity we are going to solve a problem of a particle moving in a cycloid motion. So the problem says that a particle with a charge is released in a presence of an electric and magnetic fields perpendicular to each other. So if we suppose that the magnetic field B points in the x direction and the electric field E points in the z direction, as is shown in the figure, if the particle starts moving from the rest and is released from the origin of the coordinates, what path will it follow? Well, initially guys, the particle is at rest, so because the magnetic force depends on the velocity, then the magnetic force initially is 0, and the electric field accelerates the charge in the z direction, like this. In the z direction, if we initially have the particle in the origin of coordinates, the red point, the electric field accelerates the charge in the z direction. So the charge is gonna start moving upwards, okay? So as long as the particle speeds up, the magnetic force appears and pulls the charge around to the right. So as long as as long as the particle gains velocity and is moving outwards, the magnetic force appears and pulls the particle to the right. And as faster as the particle goes, the magnetic force becomes stronger, right? And eventually it curves the particle back around toward the y-axis, so the particle is gonna move like this, okay, because of the magnetic force. So at this point, I mean point A, or when the particle is moving toward the point A, the particle is moving against the electrical force and it starts slowing down. So the magnetic force then decreases and the electrical force takes over, bringing the charge to rest at point A. So it moves like this, and at this point A, the particle is going to be at rest again. The same process starts over and over, and the particle is going to do this motion, okay guys, and that motion is called or is known as cycloid motion. So let's do some math. Because the particle because there is no force in the x direction, the position of the particle at any time, the velocity of the particle at any time can be described like this. We can write the position of the particle. We can write the position of the particle like r is equal to 0 in y plus y direction j plus z direction k. That's the position of the particle at any time, okay? These y, j, and k are the unit vectors, okay guys? And these unit vectors, basically they are pointing along each coordinate axis, okay guys? Well, now we are gonna write the velocity. The velocity, if you remember, is the time derivative of the position with respect to time. So we know that the velocity is the derivative of r, okay, of the position with respect to time. So if we write the derivative with respect to time, we get by, initially we have 0 as along the x direction plus by j direction plus vz along the k direction. So, but if we use notation, that notation for derivative, we get v equal to 0 I plus y dot j plus z dot k. Okay guys, now let's write the magnetic field. So we're gonna, before writing the magnetic field, we are gonna call this equation number 1, number 2 in this case. This is number 2, and the first equation is number 1. Okay guys, let's highlight those equations, and we have equations number 1 and number 2 are ready. Now let's write the magnetic field. The magnetic field is B equal to B direction I. Okay. This magnetic field, we know, is pointing along the x. Is pointing along the x direction. It's pointing along the x direction. So the next step we are going to take is to calculate the cross product between the velocity and the magnetic field. So this product is V cross B equal to the determinant of the matrix that we have right there. Okay, but we can write this matrix like this, right? And the terms in the matrix are the components. For example, these terms are the components of the velocity, and these terms are the components of the magnetic field. Okay, so let's write this cross product like this. What I did here is that I wrote the matrix with a repetition of its two first columns, not written outside of the right side. Okay guys, so taking the product, the diagonal product of the terms like this, okay guys, so I go in this direction with these diagonals, and I add those terms, and now we take the diagonals in this direction, okay guys, so we get the following operation. the component y dot multiplying 0 with the I component plus, right, plus let's go to the next line, c dot y j z dot b okay guys, plus k 0 0 minus, in this case minus okay, in this case it's gonna be in this direction, right, along the orange lines, orange diagonals. It's gonna be y dot b k plus the second diagonal, the second orange diagonal, z dot 0 I plus the third diagonal 0 j. Okay guys, so this term is 0, this one is 0, the ones multiplying 0 are 0, this is 0, obviously this is 0, and this is 0. So with that known, we get this, then we get that v cross b is equal to z dot b j minus b y dot k. Okay guys, and we are gonna call this equation number 3. Equation number 3. Okay guys, remember that the total force acting on the particle, is let's write this real quick. The total force on the particle, is Ft equal to the addition of the electrical force plus the magnetic force. Okay guys, by definition those forces are electrical force is equal to, by definition, the product of the charge multiplying the electric field. Okay, the magnetic force is the product of the charge with the cross product between the velocity and the magnetic field. Okay guys, so we can write the addition of these two terms like this. Total force is equal to the sum of this term with this. Okay, so we get Q multiplying the electric field plus Q multiplying the velocity cross the magnetic field. Okay guys, if we remember that for the second Newton's law, we know that the total force is equal to the product of the mass and the acceleration. Okay, so what we are doing here is this: we are taking this term that is equal to this, right? And because they are equal, we can write Q E plus Q V cross B equal to the mass multiplying the acceleration. But we know this is the mass multiplying the acceleration, but we know the acceleration is, in this case, we have two components of the motion on the plane XZ. On the plane YZ. So this is Y2 dots J direction plus Z2 dots K direction. Okay, guys. Finally, this equation turns like this: QE. Okay, we have to remember something. We have to remember that the electric field is pointing along the K direction, so the electric field is a K. We know that the magnetic field is, okay, this is, let me do something here real quick. This electric field is this term, right? Is this term. Now we have to get and write the product V cross B, and the V cross B is V cross B is equal to, according the product is Z dot Bj minus V B Y dot K. Okay, guys, so we have this and we have this. Okay, so those two terms, we are gonna replace those two terms into this equation. We are gonna replace those two terms into this equation. Let's do it. We know, guys, that we got these two equations, right? This one, and this one. And we said that we are going to replace these two equations into the one on top. So when we do that, we get Q A K plus Q multiplying V cross B, but V cross B is Z B J minus B Y dot Z dot, C direction Z, equal to M Y2 dots J plus M C2 dots K. Okay, so we get K. So we get K. Okay, here I gonna, this is K and here's K, right? Okay, so we get Q E K plus, I'm gonna take factor common Q out, okay? And I get this AQ Q A K plus Z dot B J minus B Y dot K equal to M y 2 dots j plus m z 2 dots k. Okay guys, so now the next step is separating the components. Okay, when I separate components, the equations in the equation, for example, we are getting, for example, this component, writing this component with this one, and these two components are equal to this component, okay, because we are writing the components separately. So, and the same for the other component. The other component, this one with this one. So when we write equations, the j and k components separately, we get the following equations. The equations are q b z dot equal to m y 2 dots, and q e minus q b y dot minus m z 2 dots. So what I did here is I wrote the components. Okay, I wrote the components. So this one is for the j component, and this one is for the k component. Okay guys, so if we divide each equation by m, we get the following. Q B Z dividing m equal to n, and the same for the second one, and okay, and the same for the second one. So now we are gonna eliminate m on both equations like this. This one eliminates this one, and this one eliminates this one as well. Okay guys, and when we do that, we can write the equations like this. Yes, now let's do something. Let's write the letter B on the second equation like this. On the first term of the second equation, we multiply and divide by m. So, and if we write W as QB dividing m, we get the following equations, right? And finally, we can write these equations like this: W C dot minus y dot 2 dots, and I take here's a B, factor common, W E dividing B minus y dot equal to Z 2 dots. Okay guys, these two equations are two coupled differential equations, and we gotta find the solutions for them. Alright, so we highlight them and we write the solutions for these two equations like this. Okay guys, before writing the solutions, I forgot to talk to you about something. This term W is called cyclotron frequency. Okay, this is the frequency which the particle moves or revolves. It moves in a circular path when there is no presence of any electric field. Okay, so this is defined as cyclotron frequency. So let's go to the solutions of these two equations. Okay, as we said before, these are coupled. Differential equations. Okay guys, so these are two coupled differential equations, and we are gonna solve them. So we gotta write the solution for those two equations. Okay guys, these ones are the solutions for the equations. So you may be wondering, where are coming those equations from? Okay, let's do a little I'm gonna mention something about it. The first one, okay, this equation is the solution for the y component, and this one is the solution for the z component, and they are general solutions for in this case differential equations. Okay, a coupled differential equations. But these two terms, especially this term E dividing B multiplying T, E appears because originally we have to do a change of variable for this equation. Okay, but here in this video I'm not doing that calculation, but you can write in the comments. Actually, I will write a comment of how we can get those solutions. Okay guys, so don't worry about it. I gonna write in the comments how we can get those solutions. Okay guys, so those are the solutions: C1 cosine of WT plus C2 sine of WT plus E over BT plus C3, and Z of T is C2 cosine of WT minus C1 sine of WT plus C4. So don't worry about where those solutions they are coming from. So we can talk about it in the comments, and we can do some explanation, real quick explanation about it. Okay guys, so now we need the derivatives of those equations. Okay, the derivatives. We need the derivatives of with respect to the time of these two equations, and these equations are the following equations. These equations, right? So we know that the particle started from rest at the origin. Okay, so because we know that those are the initial conditions of the problem. So the initial conditions are y dot of 0 is equal to z dot of 0 equals 0, and y of 0 is equal to z of 0, and this is equal to 0, right? So that means that the particle started moving from rest at the origin of the coordinates at t equals 0. So what we are going to do is replace these initial conditions, right? First, we are going to replace these initial conditions into these two equations, okay? Into these two equations. So when we do that, we get the following. We get the following equations, right? So this is what we get when we replace 0 into the equation for y. So when we get that, we know that this is equal to 1, cosine of 0 is equal to 1, sine of 0 is equal to 0. This term is 0 because it's multiplying 0. So we get c1 multiplying 1 is c1. This is 0. This is 0 plus c3. And this is equal to 0. So we get that c1, c3 is equal to minus c1. Okay, guys? Now we are going to replace the initial conditions into the z equation, right? So we get the following equation. Okay. This means that c2, this term is 1, right? Cosine of 0 is 0, sine of 0 is 0. So we get c2 multiplying 1 is c2, c1 multiplying 0 is 0 plus c4, and this is equal to 0. That means that c4 is equal to minus c2. Okay, guys. Now we are going to replace the initial conditions into the time derivatives of the solution. So we start with the y component, okay? So we get the following equation. And when we get this equation, we know sine of 0 is 0, cosine of 0 is 1. So we get WC2, this term is 0. And WC2 multiplying 1 is WC2 plus E dividing B equals 0. Then we clear C2 and we get that C2 is equal to minus E dividing WB. Okay, guys? E dividing WB. And now we replace the initial conditions t equals 0 into z dot equation. And we get the following equation. Okay, with this equation, we know sine of 0 is 0, cosine of 0 is 1, so we get minus WC1 multiplying 1, and this is equal to 0. That means that C1 is equal to 0. Okay, guys, we got the we calculated the constants, all right? Then with all those calculations, we know that C1 is equal to C3 equal to 0. Okay, we know that C2 is equal to minus E dividing WB, and C4 is equal to minus C2. So that means that C4 is equal to E dividing WB. So we replace those terms into the original equations, into the solutions. For example, we replace these constants, this, and this, into the equations y and z of t. Alright, so let's do that. Y dt, y of t is equal to minus e dividing wb sine of wt plus e dividing b multiplying t. So let's write a w like this. On bottom on top. Okay guys, so when we do that, we are gonna get something like it's gonna be real useful for us. So this equation, okay, we take common factor out this term. E over WB, E over WB common factor out. Alright, when we do that, we get E dividing WB multiplying minus sine of WT mass plus WT. Okay guys, and we get this equation, y of t is equal to E dividing WB multiplying WT minus sine of WT, and we call this equation number 4. Okay guys, when we replace the terms into equation z equation, so z of t is equal to c2 cosine of wt plus c4. When we replace the constants into the equation, we get z of t is equal to minus e dividing wb cosine of wt plus e dividing wb. If we take common factor e dividing wb, we get z of t is equal to e dividing wb 1 minus cosine of wt, and we call this equation number 5. So if we call this term r equal to e dividing wb, for equations 4 and 5 they become those two equations. So here what I did is I wrote the equations y and z, replacing e dividing wb, writing e dividing wb as r. Okay, and we got these two equations. So, and here I distributed this term, multiplying this one r with the terms that are into the parentheses, and we get these two equations. Okay guys, so now what I'm gonna do is this. I'm gonna take this term, okay, let's write the equations we get y of t is equal to rwt minus r sine of wt, right? And z of t is equal to r minus r cosine of wt. I'm gonna take these terms and take these terms to the other side of the equations. So when I do this, we get y of t minus rwt is equal to minus r sine of wt. Okay, z of t minus r is equal to minus r cosine of wt. Okay, guys. So now we are gonna take the square of on both sides of each. So when we take the square on both sides of each equation, we get square here, square there, square here, square there, right? This equation, basically this term is we get something like this. Basically we get something like this. Okay, guys, so now what I'm gonna do is we add up both equations side by side. So we add this side with this side and this side with this side. Okay, guys, and when we do that, we get the following equation, right? This equation, we get this equation. So what we know by trigonometric identities that this term is equal to 1. So the final equation is y minus rwt squared plus z minus r squared is equal to r squared, right? So we have that. Okay, guys, this equation, what kind of equation is this? This is an equation of a cycle. Okay, guys, with the center of this cycle is with these coordinates. Give me a second here, guys, real quick. With the center at 0 r w t r. This is the center of the cycle. Okay, this is the center. This is the x component, this is the y component, and this is the z component. Okay, guys, remember something, the center travels in the y direction at constant speed, v equal wr. But if you remember that r is equal to e dividing v w, so then we get that v is equal to wr, but r is e dividing wv. We cancel w with w and we get that v is equal e dividing v. So guys, the particle moves like a spot on a ring of a wheel, so rolling down the y-axis at the speed v. So the curve that is generated in this way is called a cycloid. So guys, this is the solution for the problem. Hopefully you like it. If you like it, please give me a like. Don't forget to subscribe to my channel, and see you in the next video. Bye.